Welcome to Retro Depot. Today we're going to be taking a look at WinCUPL or CUBL or whatever you want to call it. It's a program used for writing the JDEX for not CPLDs really. I guess, yeah, technically it has some CPLDs. But we use it for GALs, generic array logics. Now today we're going to be looking at registered logic. So it's how to use the flip-flops or the registers inside of the PLDs. We're going to start off by taking a look at a simple combinational logic circuit. So we're going to save this and compile it. It works fine, so we're going to talk about it for just a minute. So we've got D0, which is an input, and ND, which is just a shortening for not D for me. And we are saying that it is ND is going to be equal to not D0. Simple sketch. Now let's go to WinSim. Let's pull it up. Grab a design file here. Blow that up. Let's turn the grid off. And we are just going to add D0 and ND. And we're going to add, let's say 10 vectors. So if I set the value to 0 and let the simulator determine ND, I'm going to have to resize this and then open it back up, but we can see it's the opposite. We've got a low on D0, high on ND. We want to add a few little places here where it flips. Simulate it again. And one reason why I wish they would update this software, but considering that they don't make the devices anymore, I guess it's okay. Anyhow, as you can see, we just knotted it. That's all we did. So how is registered logic different? Well, registered logic is quite a bit different, so let's take a look. So with registered logic, we're going to start using extensions. And this .d is an extension here. So if we go into WinSim and we close this, no, we want to grab that same design file, but only after we compile it. So let's save and compile it first. There we go. Open it back up. Let's add some vectors here. We've got our clock, D, and let's go with Q. Okay, done. Let's add a couple test vectors here. If I set my clock high and I set my data bit low, and let's say that, give it a couple writes here. Let's test it. Okay, so we've got D0, and when it goes high and we clock on the up clock, we're going to latch that data. Okay, so that's really important. Now we can change some of the values here on whether or not this is active high, active low, but my understanding is pretty much it's going to be on the upstroke that it's going to latch that data. So well, I guess it latches it on the downstroke and then it actually displays it on the upstroke. Whatever the case, so that's how you latch data. Now it's pretty straightforward. But the problem is when you begin doing combinational data or combinational logic alongside with this. So if we were to say ND equals not Q0, because we have a feedback path, we can do this. We can save, compile, but we get an error. Check your syntax. Okay. So we get 0 warnings. So now if we close this out, and yes, you do have to close it every time, or at least I do. I don't know about you. No, open it back up though. We're gonna get our vectors back in here, or our test data back in here. Give us a couple more lines. Let's write this all high. Say that we want to write this low. Let's test it. Okay, didn't work that time. Well, why is that? Well, as I mentioned before, I'm pretty sure it latches on the upstroke. But so if you give it another little area right here, we check it again. Now we actually have that shift. So in a normal write cycle, especially on, for example, a Z80 processor or something along those lines, what you're going to see is actually going to be something more akin to this. You're going to have your data present on the address bus. You're going to have your write cycle, which is going to be, if it's I/O, it's going to be I/O request along with write. And that's going to be a pulse, and then that data is still going to be on the bus for just a moment or two afterwards. We're talking about nanoseconds, but nonetheless, it's still going to be on there. And when it does that, that's what allows it to latch. So if we simulate this again, as you can see, it's going to do pretty much the same thing. As soon as we have that upstroke, it's going to latch that data, and Q0 is going to go high, and ND is going to go low. So it's very, very, very handy. Now, something else that we can do is we actually have a way of doing, for example, clock dividers. So let's say that you have a decode circuit that is going to be decoding memory and I/O, but you also need a clock divider. So this would be an easy way of doing that. You would be able to do not Q0 then we're going to go ahead and compile this, free of errors. And if we, I don't know if I need to update this or not. No, didn't do it. Well, maybe. Hold on. Try it again. May have to reload this. Okay, yeah, so it's updated. So if we take a look at this, it doesn't matter what the data is. At this point, we're not using it anymore. Instead, we're just using the clock. So let's go ahead and close this out. No, open it back up. Just to clear out, I don't know how to really use WinCUPL a whole lot, but we're going to do the best that we can. So we're going to leave clock in there, and let's just go with Q0. And let's give it some vectors. Now we're going to set the initial value to high, and then we're just going to write this. Simulate. This is the reason why I hate WinCUPL on Windows 10. Works great with Windows 95 and Windows 98 though. Alright, so we've got this pulse, and as you can see on the upstroke it's clicking. This is the output. So it's really handy if you need to do a let's say a clock divider for a UART, or let's say that it needs to be, oh, here's a good example. So in Grant Searle's website, he has a design for a AVR video display unit. Now he's got it broken out into two. Most of you are probably familiar with this, but you have a you have 8 input lines to the AVR, and you have a available pin and an acknowledge pin. So it's a type of handshaking. And the way that it works is typically you have another AVR that's reading keyboard input, and it's sending that data over to, or well, it's communicating over serial, but it's reading keyboard inputs from a PS2 keyboard, and then also sending the data from the serial port to the AVR for the video display over a parallel port. And it uses these two signals. So whenever it has new data on the bus, it flips the signal avail, and that signals the host processor that it is has new data on the bus. And if it's a high, it just writes a low. If it's a low, it writes a high. And the AVR, in turn, when it has read the data, it flips that bit on acknowledge to acknowledge that it's read it. So if it writes a 1, the AVR, once it's done reading the data, will write a 1. And if it writes a 0, once the AVR is done, it will write a 0. So something like this would actually be a good way of doing that. And I actually have an example of that very same thing. Now, this is something in order to integrate that project directly onto the Z80 bus so that you don't need any type of serial communication in order to do it. So we're going to open this. It's going to be this AVR interface. And this is a good example because this is a little bit more complex. So no. Let's close that. Okay, so this is a good example of getting a little bit more complex. So as you can see, we have a clock pin here. We have our data lines that are inputs, so D7 through D0. We have our acknowledge pin there, which is also an input in this particular AVR, and there's a reason for that in a minute, and I'll go over that. We have our avail pin, which is the pin that will be an output and read by the AVR, and we have our Q, 7 through 0, which is our data output, so it's latching that data onto the bus. Let me close this out. No. Open. Actually, new. Let's go ahead and add this information up here. Let's give it 15. This is so that we can run a simulation here in just a minute. So we have that, and then also we have our wait signal. Now, let's look at the code. Now, you're probably wondering what this is, and I actually had that on a couple other of the examples that I had before. And what it is when you're doing combinational logic like this, sometimes it kicks you errors if you don't have the asynchronous reset and synchronous preset defined as B0. Sometimes it lets you do it, sometimes it doesn't let you do it. This is where this software is kind of clunky. Half the extensions that it says that it has do not even work with this software. Okay, so this is the reason why if you need to use registered logic, a lot of times it's just easier to grab a 74 LS74, or if you need an octal latch, a 74 574 or something like that. But either way, we can save it, we can compile it. It compiles without errors, so it's good to go. Let's take a look at this though. So it latches the data from D onto the Q outputs. The available input, it actually latches to the actual way I say that. The way avail works is it's an output. So it's actually taking its output and it's feeding the not value back into the input. Now wait is a little bit different. It's waiting to make sure that both avail and acknowledge are equal before it will go high. if it's either one of them's low and the other one's high, it's going to basically drop this to a low. And what that does, it's a automatic wait state for the Z80 processor. So in other words, you can write the data, and instead of having to poll it to see if it's done, it just puts a wait state on the processor until it does it. Now we're talking about at most maybe microseconds, like maybe 1 or 2, so you're not really losing a lot of time, and it's not going to be significantly slowing down the computer because it's not going to be writing that much data, but it still slows the processor down until you've actually had a chance to get the data out there. Okay, now let's take a look at this. So we're going to set our clock high, and we're going to set our data low, and everything else should be automatically taken care of. So if we simulate this, we get 16 errors. See what those errors are. It has to do with weight. Okay, so let's go back and take a look at weight. Yeah, looks good. So let's try clocking some data in. I have no idea why this is throwing errors because I've already verified this. I wish there was an easier way of... Oh, I guess it's control left click. There we go. Yeah, for some reason it's not producing the wait states like it's supposed to. Oh, here we go. It's because I need to set these. See, this is where it comes down to me actually paying attention. Okay, so I've set the values where they need to be. Let's simulate it. Alright. So we write a low to D0, and when that happens, it flips the avail. Okay? Now, when it flips the avail, hold on. Run this again. Had too much stuff up there. When we clock it, it does flip the avail to the other value. It takes just a moment for the acknowledge pin to read it, and then it essentially flips the wait state back up. So you have this dip in there where it's reading the data. Okay. Now, what this does is it's basically a way of using the feedback from these registers in order to do combinational logic. So the best way that I can describe it to you is you're just feeding it back into the AND OR array, and you're able to use it, the output, to determine states. Now, where this comes in handy is if you wanted to do, for example, memory banking, so that depending upon what bank was set, you could, for example, let's say that you took the top 3 address lines and you latched that data. For example, you latched a 6 into the registers. You could then feed the inputs back in and then read a 13, 14, and 15, and when the data matches, that's whenever it trips a particular chip select line. So it's just an easy way of doing it. But that's essentially the basics of registered logic with the PLDs. You just have to remember that you have to play with these quite a bit. You get lots of errors. I really don't like doing this that much, but you need to keep in mind that you may end up needing to set your asynchronous reset and synchronous preset for the pins that are part of the registered logic. Keep in mind that you can slim down your code a lot by grouping pins together like this, and just make sure that your syntax is there. You have to play with it. You have to double check your code. It can get a little bit confusing because it's much unlike any other code that you're doing. Unlike, Verilog or VHDL, where you're actually, have certain things that you're assigning. With this, you're just writing logic equations is all that you're doing, and the compiler is basically flipping those fuses on or off. So that's it for this. As you can see, you can make a pretty good little latch here for latching data onto a bus and flipping a bit. That way it knows to take that data and read it. You can do a clock divider, as I showed before. You could just do a register that you can turn around and read from at a later time. So for an example, you have that output enable, and let's say you just needed to store an 8-bit value to read back at a later time. 1 byte of memory, if you will. So you would do something like this, where you actually had D 7 through 0, and you latch that data in, and then with another chip select, you feed that back through and connect it to the output enable, so that whenever you have a certain address location that you're reading from, it will trigger that output enable and stick that data back onto the data bus from Q7 to 0. So that's about it for registered logic. Not a lot to it, but it can be confusing. It's prone to lots of errors. Even I've had problems with this. I've had working code that worked. I saved it. I opened up a copy of WinCUPL the following day, played with it, and it broke. Nothing changed. It worked perfectly the day before. Everything was saved. It's kind of hanky, and you have to really play with it. And once you have something that works and that you've tested it in WinSim, my advice would be to breadboard it, test it, by hand, make sure that everything works the way that you intend it to, and then only then take that information, or take that JDEC rather, and stick it in a working system. All right. So I hope you liked the video. That's registered logic. Been asked by a lot of people to do it. That's pretty much the sum of it. Have fun with it. I'm not going to be doing a whole lot with it, but you can do some pretty neat stuff. I've seen guys do video cards with it based on PLDs. I've seen lots of other things, but there is a practical use. So just be aware. The program is kind of hanky whenever it is throwing errors at you for things that are not wrong. All right, so I hope you enjoyed it, and we'll see you next time.